for the introduction. So yeah, first of all, right, I'm actually presenting here the work of my colleague Kirti, who can't make it today. He is actually at Design Automation Conference in San Francisco, also in some kind of dark halls all day long. But anyway, let's jump right into it. So security is, of course, a very central topic that spans a lot of layers. But what matters at the end of the day is, of course, that your application level software is actually secure. And of course, you don't really want to look at all these layers at once, right? You have different teams and different toolings to look at the different layers and not caring about the other layer. But the one thing you definitely should not do on an important topic like security is just to assume there is no problem in the hardware and live with that. So definitely should make sure that somebody, some team, and some tooling is caring for verifying the hardware security mechanisms. And hardware security mechanisms are also becoming more and more prevalent. More than half of the designs in ASIC and even in FPGA actually feature some security mechanisms. Now, security is a many-faceted topic. On the hardware side, you typically look at things like, hey, you have your secret key, and you actually want to make sure that the attacker can't really corrupt it. He can't really leak the secret key, so can actually get access to any of the secret data. And a little bit in the same area as the data leakage is data inversion. So of course, some outputs that are encrypted will contain some part of the key, but actually, yeah, they will not be able to reconstruct the key or the secret data, but it will only be provided in a inverted fashion. Now, all of this, of course, is highly complex. Even if you're just on the hardware level, right, on the big stack, it's just the hardware level, but still an SoC, and looking at the security problems in there is a highly complex problem. So you will put a decent methodology into place. Now, of course, formal verification is a technology that lends itself for its unique capability to prove absence of problems. And for a topic as crucial as security, you do want to try to go that way to really make sure there are no real way where attackers can compromise your hardware. Because if your hardware can be compromised, all your nice mechanisms on the software side, well, they are really not worth so much at all. So the design we are going to use here for showcasing the results is actually OpenTitan. Pretty sure you have heard of this in some other presentations, saw it on some of the slides and some of the booths over there. So it's an open source project focusing on creating a root of trust. So it's actually a sizable design which has quite a lot of security features in it, which some of whom actually may know a lot better than myself. But yeah, suffice it to say, right, it is an SoC with an interconnect and quite a few things acting together, and it actually lends itself nicely as something to analyze some specific security problems on. Now, what is the methodology we are proposing here? It's essentially, based on formal technology, right? So you can actually achieve these nice exhaustive proofs that certain things cannot happen. And we have coupled this with a decent level of automation, so you are not forced to do too many things on your own. And this splits then into two different, slightly decoupled apps or solutions that are involved here. One is what we are calling Analyze Architecture at Siemens, and the other is Verify Secure. Let's first look at the Analyze Architecture candidate. So what we have here is an automated tool to perform design partitioning, which can actually be a crucial instrument because typically also whoever is entrusted with doing some security verification on this whole SoC, he will not be an expert on all the different blocks and their interactions. So with an automated tool that can tell you what is the influence that a certain part has, or how can some other part be influenced by other parts of the design, and then get an automatic partitioning of the design into parts that are directly connected, parts that are indirectly connected, and parts that are actually not connected at all, can really help a lot in building a crucial design understanding to actually be able to do a proper analysis of the security features. Of course, this is kind of a structural thing only. It does not really prove there are paths and things. It can maybe actually find certain absences of paths already, because if no syntactic paths exist, of course, no functional paths will exist. But of course, the idea is to couple this with the formal power of the verify secure. And for that, it's then you that are asked to provide what are your expectations in your design, which you can then typically, you peruse the spec to figure out what is the things that you expect to happen and what are the things that you don't expect to happen. And then you could specify different things, like the path here on the upper side from D to E. Well, what you want is there should be no direct connection, so the data E is never going in a direct fashion to this particular user visible output, but it only goes there through the RSA encryption module. So yeah, you don't expose the secrets unencrypted, but only in an encrypted fashion. And similarly here, the A component down there is something that is secret, so you want to make sure that a user-controlled input cannot really overwrite it, but also that it's not possible to actually read out the output on the B port, so to speak. So that would be the typical things you then input based on your understanding of the architecture of what are your expectations for the particular design that you're examining. And then you would fire up the verify secure, which is similar to other things that you may have seen in the EDA world for data path verification. So for all the paths that you've specified, formal assertions will be generated. Some optimizations are ongoing, and then it will start fire up the formal proof mechanisms, which will then either give you a nice proof, hey, there is no path, all is good, or it will show you a path that is actually happening. Typically, you have the standard waveform debug, where you can see cycle by cycle how your source data gets to your target position. And then you can figure out at which point you actually would expect this path to be blocked and figure out what you need to do to actually make sure the data does not propagate. Now on OpenTitan, I guess the name here, I was planning to say there's some cryptic name there, but of course we all heard about Earl Grey yesterday, so yes, we have looked at the Earl Grey part, or the Earl Grey configuration, so to speak, of OpenTitan, and we just focused on the AES and OTBN modules and wanted to make sure that these are not really accessible, so to speak, or can be compromised by the other modules, so to speak, on the other side of the crosspath. And again, the analysis is this two-part thing. We can do the architecture exploration, and we can do then the path analysis, the formal path analysis. Now, this is actually summing up the thing again. So what we would expect, of course, the key manager can get there and the AES data gets to the core, but other paths we would not really expect. Of course, with a more detailed knowledge of the system, you can derive more detailed properties and paths that you expect or don't expect, but this is the thing that we used here as a test vehicle, so to speak. Now, here's then first some results. When you look at it, some paths are found, then lots of stuff is a timeout, which is kind of a quite underwhelming result. And the thing here is, this is not really following what I was suggesting, doing the analyze architecture first and then using this to prune the problem automatically. This is just kind of doing the pure force, the brute force, so to speak, application of the path analysis, the verify secure. So here you don't really get great performance out of it. You find some paths, but that's it. So let's therefore look what the other part of the equation, the analyze architecture, actually gives you. So, yeah. The thing is here is we are focusing on the AS module and what this analyze architecture then is figuring out. Sorry, okay. Slightly different animation in the version of slides I had, but anyway. Imagine there's a box here around AES key manager, the crossbar and the IBEX core and the debug module. That's kind of the partition that is directly connected to the AES module, and the other parts then, so to speak, are further away, and some of them not even connected at all, which is then information that you can automatically extract with the analyze architecture. You just input your sources that you're interested in, the AES, and if you then couple the two tools, so to speak, you get some kind of speed up. Doesn't really matter too much. It's still around a minute or whatever for proving paths and finding paths. But here you finally also can prove absence of paths. So in summary, I mean, what we are proposing is a formal-based methodology safeguarding against these any kind of attacks on the hardware side, so to speak. And this is something that actually really scales up to large-scale designs, to SoCs, if you do it smartly. And yeah, the smart part here, as we demonstrated, is done by the combination of two apps, some architecture analysis thing that kind of partitions your design nicely, and then this partitioning information can be used by the Verify Secure to get you the performance kick that you need on your modern SoCs. So of course, I mean, yeah, we try to keep up on the crazy pace on which designs are getting bigger and more complicated and the problems are getting more intricate. And yeah, also we want to make the things more easier to use on the methodology side. So I guess that leaves a few minutes for questions.
Plenty of time for 3 or 4 questions, if there are. No questions? I do have one question.
Okay.
Okay, so you mentioned, I mean, OpenTitan is well known for the side channel resistance as well. So I'm wondering how your tool may help also to identify or at least make sure that this side channel resistance is well implemented. I mean, if can help, or if you can comment on that.
Right. There is, I mean, a slightly different spin for these side channel attacks. So there we are collaborating. I think we have a presentation on the research base from University Kaiserslautern, which we are in a way working on productizing, which is really focused on the particular side channel attack thingy, or you call it the transient execution stuff. Exactly. So I mean, there we are. We don't have a product out yet, but we are working closely with academia and try to get a first prototype out soon, so to speak.
Okay, thank you very much. No more questions? So, if not, a warm applause again, and yeah, we go to the